Hello, 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 and welcome back to sort of a half episode of Kerbal Space Programming. Kevin here, and I wanted to go through the scripts that we used in the previous episode, in episode 37. I've got the folder open here in this project drawer, and as you can see, there are a bunch of files in here. We have the craft file, which is the ship itself, and there's a README, which I put in all of the episode scripts that links to the actual video. But we actually have, six separate different .ks files that were a part of this craft and part of this mission, and most of them were things that we've seen before. So I didn't want to kind of stop and pause and go back and go through everything during the mission itself, because I thought being able to do kind of one-shot mission is pretty exciting, something we've been looking forward to being able to do for quite some time. And obviously we've spent a lot of recent episodes trying to optimize like individual features, and you never really get to see how it all gets put together. So I am away at a conference this week and figured, hey, this would be a good time to, since I don't have the opportunity to work on scripting for episode 38 just yet, I figured I'd go ahead and actually review the code itself. And so you see, we've got a bunch of stuff that looks semi-familiar. We've got, a maneuver library. We've got a mission runner library, which we talked about before. We've got the hill climb library, which we talked about recently. The transfer library we've got recently. The only two things that are really uniquely different are we have a boot file that's just for this mission, and we have a mission file, which is just for this mission. And you see, now we've actually got 6 files. We're kind of pushing the limits of what we can do in terms of file size. If I go ahead and just do a word count or a character count over the .ks files, you'll see there's, the boot file is relatively small, but pretty much everything else is kind of getting up there, and we're down to 13,000 characters. I had to expand out the CPU core that we were using, because we're using the small core, and that caps out at 20,000. So if we were doing anything, hugely more complex than this, would have to either break things out into, delete this half and now fetch new files from mission control or something like that. So let's actually start out. I'm going to go ahead and open up the boot file so we just see exactly how this is structured. So this is the way that I've set up the boot script. And basically it says for every dependency in this list of dependencies, if it doesn't exist on the hard drive, go ahead and copy it from the archive volume. So this should only have to happen the first time. This is just saying these are all of the libraries that we are going to require because we need them as some part of our mission. And I'd love to eventually abstract this out. So in addition to just copying it, it'll go ahead and run them too. But at the moment, you can't do things like run that. It gets confused. I know that's something that is potentially going to change at some point, though it'll likely have to wait until after the next KOS version release. But anyway, so we go ahead and we say, here are the dependencies, the libraries that we're going to require, along with these version numbers for most of them, because I've been making small adjustments and bug fixes and stuff. I want to make sure that things don't get too out of control. So we go ahead, we've got these libraries, they're all running, and you'll notice that just as with a lot of these recent things, I've been putting these inside these little curly braces, and this means that if we ever happen to declare something, inside here, if we have some function, it's not going to mean that if somebody else says foo somewhere else, we run into conflicts. So going ahead, load the dependencies, we run them all, and now I say, all right, we're just going to say run mission, and I'm going to say Herald mission sequence and Herald mission events. And this is actually coming from the Herald mission.ks file itself. The rest of these are utility libraries. This is the one that actually describes what we intend to do for our mission. So let's go ahead and actually open, let's go ahead and actually open that up. So the Herald mission file, close you. All right. So Herald mission script. First thing we've got is we've got some constants that we're setting in here. And I guess I should also mention that because we've got these things in curly braces, I've got all of these characters indented. These all count as characters against that character limit. So I imagine if we got rid of those, it'd save us maybe 1,000 or so across all these files. We say, okay, the global thing, the thing that we want to actually expose outside of these blocks are the Herald mission. And we're providing the sequence, which is a list of steps that are part of our mission, and then the events. Now, if you remember in previous talks, we talked about the idea that we would have a sequence of things that runs in order, and then we might have events that try and run as frequently as possible. So for something like, make sure to deploy the solar panels if we run really, really low on battery power, or disable the antenna if we run low on battery power, or turn it back on if we end up with enough battery power, things like that. In this case, we don't have anything, but I wanted to keep it in here just to be safe. So that's what we've got. So we've got the sequence, which is we've got to do a pre-flight, we've got a launch, we've got an ascent, we've got a circularize step, we've got a perform transfer step, a perform capture step, an enable antenna step, and then we've got idle, which is just the last thing that we're going to do. So let's look at what these steps actually do. So pre-flight, it's going to do that whole set ship control pilot main throttle to 0. It's going to lock the throttle up to 1, lock our steering to up, and then it's going to wait 5 seconds. And then it's going to go, all right, go ahead on to the next step. Remember, we have abstracted out all of this whole event loop thing. We just said, all right, you're going to take in a parameter called the mission, and you can just go ahead and call next when you say, all right, don't ever call me again. I've done my job. So that's what we've gone ahead and done here. So now we've got the function launch, and okay, yeah, you see I've got a note in here. We go ahead, we stage, and we wait 5 seconds. This is just kind of copying stuff that we had done for our genetic algorithm test. We're saying we've got our percent altitude, which is the current altitude divided by the target altitude, which was 100 kilometers. And I pulled out the values that we got from our genetic algorithm runs, and it said, here's the target thrust to weight ratio that it was optimizing for. It was 8.26. And pretty much constant. I think we had these in forms of a function of a times x to the b plus c, and we were saying you could go ahead and tune these values. And basically, what it says, c was 8.26, and b was 0.0, pretty much nothing, or yeah, it was something like that. So it was like 7.26, and then a was 1. So x to the 0 becomes 1, multiply that by 1, you get basically a value of 8.26, no matter what value of x you put in for here. So it pretty much found that there was no benefit to trying to limit our thrust during our flight. But, just for fun, I decided, okay, we'll go ahead and keep that in here, lock the throttle to the target thrust to weight ratio divided by the available, and then make sure that it's not, that is between 1 and 0. But I put the note in here that honestly, we should just keep the throttle locked to 1 and just go with it. But we did what we did. The target pitch though did actually have, a more reasonable curve. So this is negative 100. So we start off with 88 degrees, you're pretty much at 0. And then over time, we start to add in this negative 115. And that kind of describes the curve of our pitch off of the horizon over time as we get up to altitude. We lock steering to the heading of east and that target pitch, and we say, all right, once we're done with that, then go ahead and go on to the next step. Next step being the ascent, and all the ascent is doing, most of the time it's doing nothing. It says finally, okay, if the apoapsis is greater than where we're, than our target altitude, go ahead and throttle down, lock the steering to prograde, and wait until we're out of the atmosphere. And the reason for this is that the next step that we're going to do is the circularization step, which involves setting up a maneuver at apoapsis. We didn't quite want to set up a maneuver while we were still in the atmosphere, because then the apoapsis changes slightly, and figured, hey, we've got enough lead time, we can go ahead and do that. So this next step is circularizing, and here's what we're doing. We're doing the same sort of hill climbing stuff that we've done in the past. We're saying go ahead and seek a delta V value. So we're passing it just a single value. In the past, we had it, we passed a list of 4 values. So, a time to start a maneuver, and then the delta V's in 4 directions. Here we're saying, don't bother checking all those other directions. All I want to know is how much prograde delta V should we apply to a maneuver. So I say, okay, set the delta V to hill climb, seek a delta V value based on its circular fitness, and use a step size of 100. So what it's going to do is it's going to go ahead and say, let's create a maneuver node at some specified time with 0 radial, 0 normal, and 100. I'll say, is that good? I'll say, what about negative 100? And if it decides that, okay, the cursor's jumping around, and if it decides that 100 is good, okay, what about 200? Is that good? Is that better? And it'll jump around until it finds the best value of that. And I say, okay, once you found that, then go ahead and step by 10, and then go ahead and step by 1. And the result, as you saw in the past videos, that this ended up going ridiculously fast. It just, jumped, because it's only checking that one value. It jumps to the nearest 100, then it jumps to the nearest 10, then it jumps to the nearest 1. And the circularization fitness is just, hey, how eccentric is the orbit? Are we close to being a circle? If we are, then it's better. Then once we've actually got that delta V, we'll say, okay, we're going to create a node at time seconds plus the time to apoapsis with 0 and 0, and then that delta V value that you found. We wait 0.1 second. You'll see a lot of 0.1 waits in here because occasionally as you're adding maneuver nodes, things get, it doesn't quite pick up that it got added right away. We're going to call our maneuver library and say, go ahead and execute. That's what our maneuver library does. It executes nodes. Wonderful. It takes an optional argument of true to time warp, but we're not passing that in. So we're saying, just go ahead and execute the node when you get to there. We're going to turn on the panels. Once we've done that, we'll lock the throttle to 0. We waited a second in stage and wait, and then we say, all right, we're done with the circularization. Now the transfer is very, very fun. It's probably the most complicated part of our script, but this actual step ends up being very small because we've got that abstracted into libraries. We say, okay, we set our local MNV. So the local node is seek a transfer to the moon with a target of 40 kilometers. Go ahead and add that maneuver and then say, all right, the maneuver library, go ahead and exec that and use time warp to get there. And that's all, just a few lines here. Really, really nice and simple. We've got perform capture, which is, so we wait until the body is the moon. We say, okay, wait 30 seconds after that because occasionally we might cross just barely over the sphere of influence and then back out, and KSB gets confused about whether we're around Kerbal or around the moon. So we go ahead and wait 30 seconds for 30 seconds after we detect that we're around the moon. We go, okay, we're going to do the same thing here. We're going to find a delta V that gives us a circular orbit. And we're going to do that same trick of just stepping by 100s, stepping by 10s, stepping by 1s. And of course, in this case, it's going to find negative prograde delta V. We go ahead and add that node, but to periapsis. We say, all right, wait a second. Tell the maneuver library to go ahead and execute the next node. And we'll say, yeah, go ahead and use time warp. And then we're done with that. Enabling antenna. We've done this plenty of times in the past. We're just going to get the part by the part name. We're going to get the module remote tech antenna. For the dish, we go ahead and activate it by setting its target toward Kerbal. And for the Communotron, we just go ahead and activate it. And this means that now we have a nice little, the start to a satellite network around the moon, which is great because we didn't have that before. We had one thing that was there, it was on the surface of the planet. It was just sometimes in range, sometimes not quite. And then we have this idle function, which is just, we're done. It's not going to go ahead and call mission next. It's just going to be, I'm the current state. And then down here at the bottom, we've just got these helper functions. So we've got things like the available thrust to weight ratio, which is just math and stuff that we've done in the past. We have two libraries here that should be merged. They're not entirely great. These are the fitness functions for our two circularization maneuvers. One was circularizing at apoapsis. The other one was circularizing at periapsis. And so we're saying, all right, you're taking in a parameter, which we know is just going to be a list of one element. We're going to say, okay, let's create a node at apoapsis with 0, 0, and then that data. And then we'll give it a score that's based on its eccentricity. So if you've got, remember, an eccentricity of 0 is a circle. An eccentricity of 1 is, almost transferring, almost out of the system. Yeah. So we go ahead and say, if you're almost out of the system, if you've got something that's, not spherical at all, then we'll just go ahead and say -1. If you've got something that's halfway toward being a circle, it's 0.5, and you've got something that's a circle that it's 0. And so the best score that you can have here is 0. So we go ahead and just say, there is our fitness score. Go ahead and remove any nodes that we've added and go ahead and return that fitness score. This one's doing the exact same thing. The only thing is that the node that we're testing against is at periapsis. So it's probably the case that we should actually merge these functions into one and just say, here's the way that, here's the actual time that you should go ahead and pop in for the node. And then, just the remove any nodes function, which just says until we don't have another node in our flight plan, go ahead and remove one and then wait a second. So, aside from that, I don't think there were very many changes. Let me think here. The mission runner, the mission runner has a lot of comments in it because that's something we did back when stuff. So it has a bunch of stuff that we didn't end up using. So things like, I want to switch to a specific run mode or things like that. We've gone over that all in the past though, and there weren't any changes to that. The hill climb library, this is exactly the same as it was before. See what files I'm going over. Oh, the maneuver library. So this is updated a little bit since, updated just a tiny bit since to actually put this thing inside these curly braces and stuff. The one change is actually the pull request on GitHub is that when calculating the amount of time that it'll take to complete a maneuver, actually let me look up the name. All right, yeah, so it's GitHub user Blink 2007 made a small update pull request for the actual maneuver library, and this basically goes through and it says it computes. So we had initially just assumed that there was one engine and that was the one that would be firing. He actually updated this to say, all right, well, for all of the engines, if it is ignited and hasn't flamed out, we're going to assume that this is going to contribute to our thrust and our average ISP. And so when we go ahead and return this big ugly formula that tells us how long it's going to take for us to complete a burn, well, we can go ahead and actually average out those engines to do that estimate. So really appreciate that. Wonderful contribution. The maneuver time is just used so that we can determine when we need to start firing when we actually execute this maneuver node. So this is from way back, like episode 10 or something. We actually did this. Really just minor refactored this into its own little library so that it's using the new wonderful syntax of function delegates, because I really like this. I like the idea of we're not going to pollute the global namespace with these words that we might use in a bunch of different files, because this gets more and more dangerous as we expand out our library to do more things, is that maybe we might have some word, and actually I kind of ran into this with the word maneuver, where we're using this in a bunch of different places, and we can end up with collisions if we're not careful. So let's see. Yeah, I guess I did tweak the transfer library just a tiny little bit. We have this seek function. Oh, yeah. Okay. So this is a small change that I made from the episode before. So I have this thing here until false. What we had initially when we were first writing this was something like this: set the data to hill climb, a transfer fit with a step size of 10. What I decided was that this didn't make a ton of sense, and in fact what we needed to do was because, well, I bumped it up to 20 just to make it run a little bit faster, but what we discovered is that, in particular when trying to transfer to minimus, is that it's possible that we get stuck in a valley. That because of the way that KSP estimates closest approaches and stuff, we may find ourselves in a position where there is no direction where we can go that improves our situation, but we still haven't gotten an encounter. So I said, okay, until 0, we're going to go ahead and set our data to hill climb this according to this transfer fit. And we say, okay, if the maneuver that we found does transfer to the target body, then great, we got it. Otherwise, we're going to set our attempt to attempt +1, and we're going to say, all right, set the data to starting data, but with a new attempt value. And what the starting data is now going to do is going to say, all right, and this is down to, well, I can split this and we'll jump down to the bottom of the file. Well, where is it starting? There we go. Starting data. Takes in parameter attempt and says, all right, the maneuver that we're going to start with and try to improve upon is current time plus the maneuver lead time times the attempt. The maneuver lead time is, I believe, 10 minutes. So we're going to say, okay, our starting maneuver time that we're going to start testing with is now plus 10 minutes. And then if we get stuck, if we don't find a node that actually transfers to the target, we're not going to give up. We're just going to say, all right, we'll start over, but from something that starts at 20 minutes. And we'll continue to do that indefinitely. And with minimus, because the moon kept getting in the way and kept getting to a point where we would get closer and closer, but then if we tried to get closer still, would just collide into the moon. We ended up getting to a point where we were looking at something like now plus 3 hours. And at that point I said, let's just actually transfer to the moon for this test run, and we'll worry about minimus later. So anyway, that's the getting our actual encounter from the maneuver. Then we go ahead and we refine it based on the inclination, and we're going to do that whole step size down thing. So we step size by 10, then we step size by 1, and then we refine by periapsis. And these are using different fitness functions. The way that these fitness functions do check if you've lost the sphere of influence encounter, and that says if you've done that, you have a terrible score. So it'll only try and adjust the maneuver to improve the inclination and then to improve the periapsis. So we want to make sure that we have a prograde orbit, and we want to make sure that our periapsis is close to our target. And as you saw in the video, we ended up with a good orbit that had a periapsis of 40 kilometers, which is great. We remove any nodes, we return that node. So yeah, the transfer fit bases things off of the closest approach. the negative value of the closest approach, because we want our closest approach to be 0 kilometers. And then the additional functions, the inclination fit, just looks at the next patch inclination. And it says if you don't transfer, then your score is negative infinity, which we've just defined to be very, infinity is just a very big number, because there's not a real infinity in KOS. But we're just going to say, your score is the negative of your inclination. And for the periapsis, very similar stuff here. And I've got to note that some of the stuff could probably be abstracted out because it is all very similar. Just return the difference between the target periapsis and the periapsis, because we want that to be 0 as well. And of course, if you didn't transfer, then that is negative infinity. And then we've gone over the closest approach stuff in the past. It's doing some comparisons of stuff based on trying to estimate the rate of change, which has a little bit of variance, and that's why occasionally this thing can get stuck. But anyway, so lots of files. Hopefully we shouldn't actually have to do much adjustment of these libraries going forward, or if we do, they should be relatively small. That basically when we're doing new stuff, we'll just go ahead and create a mission file that describes the sequence of our mission and potentially some events if we have things that need to happen kind of on a regular basis. And then we can go ahead and just create a boot script that loads up all the dependencies, runs them all, and then goes ahead and say, all right, you've got your mission. Let's go ahead and do it. So I will hope to see you all for the next episode where we can go ahead and advance our awesome Project Athena stuff and hopefully get ourselves something landed on the moon, in progress for getting something landed and coming back. So I will hope to see you then. Cheers.